All right, so the first speaker this morning is Professor Schmiedmayer from Vienna, and he arrived last night, so thank you so much for making this long trip.
I hope I didn't get this contract last night.
Well, probably not, because they would have stopped you on the way.
Okay, yeah.
But we really appreciate you coming all the way and giving us a series of 3 lectures on hybrid quantum systems. So thank you very much.
Yeah. So
about 1 hour or so.
Yeah. Don't worry, and interrupt me anytime.
Oh, I should tell all speakers that you cannot use a laser pointer here.
I know.
So you have to use a microwave.
Yes. Yeah. Okay, so yeah, I'd like to come to desert cases or something. This picture was taken last summer in Aspen.
You took it
on the premises of the physics center.
Wow.
So yeah. And if somebody wants, I brought some good binoculars with me, and we can watch. There's a comet to watch, but the binoculars are in my suitcase, and it's still somewhere. That's why I came in late last night, because it was all this. Good. So I will try to give an. Since I'm the very first one to speak, I thought I'd give a very broad overview of what is something that is called very colloquially as a hybrid quantum system, because I think there's no real good definition or something. Making hybrid quantum systems came out of an observation that certain quantum, when you started to do something like 10 years ago, when you started to do various types of experiments with quantum systems, and some systems are better than others for certain tasks. And there was a question, how can you connect all the different quantum worlds? And one of my students found this picture, which I thought is fun. It's a hybrid fruit, so that we should have a hybrid.
Yeah.
Hybrid quantum system. So we see that a few times on it. So my lectures will be basically, the first lecture will be mostly just giving a very broad introduction of and one view of what is a hybrid quantum system. It will not be going in very deep, but because I think that many of the other lectures will go into very specific systems much deeper, and they will hear the physics much more. So I want to give a very broad overview also on the challenges of what is there. And I will talk on my second lecture on the connection between photons and atoms and spins, which is, how to make a quantum memory for photons and how to make quantum repeaters and things like that. And I will talk on the third lecture something about coupling microwave circuits to spins, which is having superconducting quantum circuits. And some of our experiments, some other experiments that came out in the last few years. So, and if anybody wants to talk, I will not talk anything about non-equilibrium quantum physics, which I usually do. So my first lecture will be, how do we connect quantum worlds? Okay. So how do we connect quantum worlds? I will start with just saying a little bit about what are the strengths and weaknesses of various quantum systems, and then give a very broad overview of various techniques for connecting them, either by direct coupling or by cubic transfer, and then give a few examples in the end. So let's start first with the quantum worlds. And there we have, you go up and say you have, there's various types, there's many different experiments that came up lately, in the last more than 20 years. It's scary.
Yes.
Yeah.
Yes.
It's really scary. I was used to that. A new system came up when you start, and a new system comes up every year. You find it fascinating, but then you go back and say, oh, these are the new systems, and you find out that all of them exist since 20 years, and it's a lot less. It's horrible. Yeah, this is much more than 20 years. Yeah. So but you have ion traps, you have superconducting qubits, you have quantum dots, you have single spins in quantum dots, you have ND centers or defects, you have QD, cold atoms, photons, and all those different things. And the question I will ask is, how can I connect them together to make some kind of a big you know, integrated quantum device? And what's the physics behind there? And as you will see, is that, you know, we are very far away from really, you know, making big devices that can connect them together. And there are many challenges to be done. And so there's also things which are up for you guys to do, you know, both theoretically and theoretically. So photons are beautiful if you want to communicate. Yeah? If you want to send a quantum state somewhere, I think the best thing is you send a photon, otherwise it's hard to carry an electron spin or something. Even though, you know, and like xenon spin or something you might be able to carry around, but photons are much better. Photons come in two different kinds where you can do quantum information or quantum experiments. One is, you know, have discrete photons, you have single photons. You send a single photon, and if it's single photon arrives, and you didn't do any bad things on the way, and you can do very clever things by sending them to two paths, and Nicholas designed beautiful experiments so that they can send photons of 100 kilometers of fibers and still have their quantum states. Then there is a different set. You can use continuous states, continuous variables of electromagnetic light, where you squeeze light and use continuous quantum variables, whereas a completely different set of experiments. And, you know, probably we see in now and in the future that these two things come together. The problem is that you can make very strong, very highly entangled light in here. Here it's very difficult to get more than 10 particles to be entangled. But on the photons, you can have your most beautiful technology, which is integrated photonic technology. You make circuits and do things like that. So they are great to send somewhere, but they are very difficult to keep. Yeah. So there you see you have a problem. You wanna have one of the challenges in doing experiments with quantum hybrid systems will be, how do I store a quantum state of a photon somewhere where I can keep it for a long time? Or how do I transfer a quantum state of a system like a superconducting qubit or an atom or something into a photon so I can send it somewhere so that it can again be received at a different place? The second part are atoms, ions, and molecules, which are you know, for me, the atoms were for me the ultimate quantum systems where all quantum physics was developed from. Now, in recently, you know, you have all these beautiful physics of degenerate quantum gases, of atoms in optical lattices, atomic clocks who give you the ultimate precision. You have ion traps, which are ionized atoms in a trap, and you have, I think the best quantum operations you can do are in an ion trap. They have very long-lived storage. They have very, you know, there's a beautiful technology out there, and you can do many things with ions. There is something which has huge potential, which is polar molecules, because polar molecules have, as we will see, one of the important things is you want to connect. If you want to connect two systems, you have to have a reasonably strong coupling, and polar molecules within neutral atoms have coupling only with a magnetic moment, so it's a very weak magnetic coupling. Ions have a coupling with a charge directly, and polar molecules have a coupling which is with an electric dipole moment. And so that usually gives a much stronger coupling with a magnetic one. But they are much harder to handle, and so they're much more difficult to experiment with. And then, of course, all of the systems have nuclear spins, and nuclear spins are for me the perfect way of really storing quantum information. And you can do that in an ion, and you will see you can do it in a solid and keep it for minutes in there. And then there is with atoms and ions, there's a technology which was developed in the last 10, 15 years, which is basically you can make an integrated circuits which you use for manipulating atoms and ions. So first was the atoms, and then the ion trappers took our concept and put them into, we can have microscopic traps which can manipulate single particles and ions in an extremely robust way. And So we can also bring atoms and ions on a platform which can be easily connected to other things like fibers and stuff like that. Then something that in the beginning when I started doing quantum experiments, solid state was something like the bad area you didn't want to go to because it was too hard, it was too messy, it was completely, you had to look in the time scale of picoseconds and femtoseconds to see things. I think this thing was the biggest advance in the whole field, because they are now superconducting, they are now solid-state devices that really compete with atomic physics devices, and especially superconducting qubits and electron spins in solids like in the defective diamond. They are fantastic quantum systems, and superconducting qubits and circuit QED, a combination between cavity quantum electrodynamics for microwaves and superconducting quantum circuits together, in that sense, are now probably a technology that is very close to be on par with diagrams on what they can do. And so this is something that is really fantastic work. But superconducting qubits was also one of the starting points of developing hybrid quantum systems, because these superconducting qubits had lifetimes of about nanoseconds, and you wanted to store your qubit somewhere. So the first of these things that I will show you that was, how do I find a quantum memory for a superconducting qubit? How can I store a photon, a microwave photon, in an ensemble of spins or in an atom or something like that to make a long-lived quantum memory? So this was maybe more or less the starting point of the whole system. So there are, you will hear lots of defective diamonds, I think, here. You will hear, I don't know if you hear so much, but there's electron spins in silicon, which are now amazing. Silicon, they can make now, one of the big advances was all the problems with coherence time in solids was based on that there are nuclear spins in the solid. If you take carbon 12, which has no nuclear spin, or silicon 28, which has no nuclear spin, you can have amazingly long coherence times. And I think it's now, experiments start now to get hard, because, not because of the physics, but because it takes a long time. I think that the lifetime of an electron spin in silicon is now 30 minutes. Yeah? The lifetime of a qubit in silicon is now 30 minutes. And that's amazing. Yeah? That's really, really amazing. And so you start getting many different things to do. And then there's, in mechanics, there's another thing in solid-state physics, which I also put in here. Maybe one needs to put them in a completely separate system, which is called nanomechanical systems. And you will hear a lot in lectures here about nanomechanical systems, which are very small mechanical oscillators, which come into the quantum limit. And they are also, it's basically, looking at, if you said before, the atoms interact with photons, and here in the nanomechanical system we say you have now a photon. A photon is a quantum object. Yeah? And this photon as a quantum object can also couple to many, many different things, and this is a nanomechanical oscillator from Schmiedmayer, or these are nanomechanical oscillators, which is a toroid oscillator, and there are many, many different things, and Clarence will talk a lot about nanomechanical systems and stuff. And of course there's still NMR, nuclear magnetic resonance, if you want to connect this with. So you have all the different standard quantum systems, and each of them has advantages and disadvantages, which I think is best connected to something that Rob Shortkopf and Steve Gervin, something like now 8 years ago, put together in a Perspectives article in Nature at the time, where they said, okay, you have some of the containers like a nuclear spin, an electron spin, an atom or a molecule, or a Rydberg atom, or a charge qubit at that time, or a transmon qubit. Yeah. They have different interactions, which is, these have magnetic moments, and these can have electric moments, like a dipole moment is 1 dBi, typically 1 dBi of a polar molecule. The Rydberg atoms has about 1,000 dBis, and charge qubits can have hundreds of thousands of dBis, effective coupling, dipole moment coupling. So these systems, these are all, all of them as a two-level system. Yeah. So basically, we view all of them as single two-level systems. So they couple, then they couple electric, they couple magnetically. then usually these things are extremely small, and it starts to become relatively large. And large qubits now, sometimes they're even larger, these transform qubits. And these couplings are very slow. So here you have, with nuclear spins, you have very, very slow couplings. With electron spins, you have higher couplings to magnetic fields. And these are couplings that are made to a microwave resonator here, which, because Rob Sherlock and Steve Gerwin were basically made this superconducting cavity, superconducting circuit cavity. And you see that atoms and molecules, these polar molecules have larger coupling strengths, and superconducting qubits are very fast, but also the coherence times are very short here, and coherence times are very, very long here. For nuclear spins, you can have hours of coherence times or more. So you see that you have a system that, if you want to operate something, we do very fast operations, you do something here. But if you want to store something, you have to get it to here. And so you want to see, can I transfer things over or not? So if you want to build some kind of a quantum technology or quantum devices, yeah, that one question is, why do you want to do that? And there are some reasons that quantum physics promises, huge advantages in computation, communication, measurement, and metrology, and things like this. And maybe you should put in there gaming, quantum games, or whatever. So many other things you can think about it. But for me, this was never the real motivation. The real motivation was just understanding, how does a very large quantum system behave, and why is our world classical compared to quantum mechanical? And so, but to obtain this quantum advantage, one really needs to keep the system quantum coherent, or at least parts of the system quantum coherent. I think it's not completely clear if you have to keep the complete system quantum coherent, or if you have to keep these systems quantum coherent that you need for your operations. So there's lots of open questions also from the theoretical point of view. I think really the thing where you have to, one of these large quantum systems that is coherent is nothing else than a really big Schrödinger. So this is a picture I stole from one of Peter Zoller's lectures. Okay. So, or is either Peter Zoller or I don't know.
I don't know who used to read from.
Yeah, so that's one of those. So basically we have to get rid of the coherent interaction with the environments. And also one of the problems is that these large systems, we have to always think about, have a very, very dense level structure. And a very dense level structure is extremely hard to operate on, because you don't want to mess and mix these levels. So in one sense, from that example here, you see already building a large system and just connecting everything together will get you into a mess, and will get you into something that looks classical. Yeah? And when we do in my other life, I do experiments trying to find out how does quantum systems behave if they're out of equilibrium. Any system you want to operate something, if any system that is technology is extremely far out of equilibrium. And we see that even the systems of a few hundreds or few thousand atoms, if you have them even completely isolated, in the end ends up looking like, for all practical purposes, like a classical statistical ensemble. So you really get out classical statistical physics without any using of any environment, anything, just because of the complexity and the density of the structure. So you have to get rid of it. So you don't want, you want to have large systems that can operate, but you don't want to put everything together into a very messy system. So yeah, quantum interaction tells you, the promise is that they keep a quantum system basically coherent, quantum coherent for infinite time. The requirement is that I can fulfill quantum operations, preparation, measurement, and quantum gates, and other things, with a high enough fidelity. And these fidelities, depends on which process you use. They are, they in the beginning where you have to have a fidelity of 99.995%, and now it's something like 99%, and if you have only certain errors dominating, it can be 98, 97%. So, but it will be, I think it will never be something like 10% or something like that. That you have to have the very high fidelity, and when you get with that, you get an enormous overhead. And the factor 10 to the 3 is really a very, very optimistic estimate. Yeah? So if you want to keep a very large, and by the way, quantum error correction is known for a very long time. The first calculations of what you really need for a specific technology to build a quantum error correcting circuit were published in the last 2 years. There's one for NP centers and one calculation for superconducting qubits, yeah? Which really go through all the nitty-gritty details. And for our thing, we did it for nuclear with some informatics guys, and basically you need to do simple operations. You need 10 to the 10 physical systems, and then 10 to the 10, and it's crazy. It's completely crazy. It's completely out of the question. Yeah, at least for now. Yeah.
But do you see a way to get better?
There's one way to get better, and one way is that most of this comes from. That's what the quantum informatics guys said. Most of this comes from that you use a circuit model, and in the circuit model there are certain operations which are the pi/8 phase shift that you need for doing the thing, which have a huge overhead to do them exact enough. Yeah. So I think 95% of the time it spends the computer will spend in doing a pi/8 phase shift.
Exactly.
Yeah. So, but there are things that okay. I mean, there will be, and there was, for example, there's Matthias Theuer did a lot of work on what it needs, and he was able to, with very clever ways of looking at specific systems, to speed them up by factors of the algorithm, and factors of hundreds of thousands, and things like that. But so to build a fault-tolerant quantum system in the near future, I think is a large fault-tolerant quantum system in the future. I think for me, it's going to be. It's a nice goal, but it's like, you know, for me, it looks like, you know, Babbage knew how to build a computer, but he had to do it in mechanics, and, you know, he would never be able to do it. This machine would have worked if he had a good enough mechanical technology, but it was not the right type of system. And the question is that, what is the right type of system? So I think we don't have the transistor or things like that, which is that part which make really electronics fly. But maybe, you know, I think the best systems can reach this threshold at a single system level, but not at, you know, if nobody knows what happens if you put them together. And so pooling the strengths of different systems, I think these hybrid systems would help also enormously in doing that. Now, the idea of doing really hybrid quantum systems came out of that, take the different quantum systems that have different strengths and weaknesses. Usually we have coherence times versus operation time. If operation time is very fast, then coherence time is also very short usually. So you want to have something for memory, which is a very long coherence time, but you want to have something to compute, which is very short operation time. You want to have something which is an extremely good readout, but you also want to have something which is stable. Usually, if you can very easily read it out, it's very difficult to keep it very stable. If you have something that is very good for storage, it's very difficult to connect to. You know, if it's something, and usually operation and storage are something that is not really geared to if you want to communicate with something else. So you have to bridge these things, and I think there the quantum hybrid systems really fall into the question. And so what do we need is we need to connect quantum systems in a way so that they can pool their strengths and overcome their weaknesses. Yeah? And they give function to a system that it does not have. Like it could give you a readout to a sensor. There's beautiful experiments in ion traps now where you have one ion which is a clock ion, but which is very difficult to read out. And by quantum gate operations, you can transfer the quantum state of that ion into another one which is very easy to read out without disturbing this ion. This is one example for example. That is these quantum information-based clocks, which are unplugged and these guys are going to build. As long as it's quantum communication to stationary quantum, you have some stationary quantum processor, and you want to connect them together because you want to maybe send a message, a quantum message, one to the other. So you need them together. There's many other things you can think about. And I think, you know, coupling the systems together would really enhance the capabilities. Now, the question is, how do we do that? How do I connect quantum systems? There is, I think for me there are two different ways, and I will give you in my two lectures, the other ones, an example of each of those two. one of the things is that one question is that, connected by teleportation, you can entangle a system, like this is an EPR source, you can entangle two systems. And you can do that probabilistically. But if you have to know that when you entangle the two systems, then they are entangled. And then you do a measurement on one system, you can transfer the information to the other system. So this is, you don't have to have a direct interaction between them, but you have to have some way of entangling them. And then you can write something into this. For instance, if this is a system which is very long, it's a nuclear spin in an atom or something like that, and that other system is a photon, I can make a balanced measurement between the photon and an incoming quantum information and write it this way onto the nuclear spin. So the nuclear spin does, during the time it needs to have the storage, it never ever has to interact with something else. Yeah? So you can really write the information in there, and I think this is one way. It's connected by entangling and teleporting. It's one way. And examples are, for example, this thing. You take an atom, this is a rubidium atom, and if you prepare your system initially in that and F2 FF equals 0 state, and you excite it with a laser to this state, and it emits a photon, it can be a plus or minus, sigma plus or sigma minus photon, and then the atomic state, the atomic spin state, is entangled with this polarization of the photon. And this polarization of the photon you can then use to teleport the information from outside into the nuclear spin. Yeah? Or this is then from an experiment of Krempe, but there are many others with people in ion traps and things like that. Or the other ways you can use it, you can write a spin wave into an atomic ensemble, yeah, and you write it into two different with two different k momenta. Then have a spin wave which is connected to either this photon being emitted or this photon being emitted. If you combine them on a polarizing beam splitter cube and then a half-wave plate here, the polarization on this photon is entangled with the k vector of the spin wave. And this k vector of the spin wave is then a quantum bit, and you can write. It's basically a spin wave which is superposition between two nuclear spin states, and then you can write that. You can use again that to teleport something into a nuclear spin state. And this is from some of our experiments. I will tell you then in my second lecture. So this is the one thing: is entangle and teleport to connect. The second one, to connect, is directly coupling two systems together. And as I tell my students always, you can understand 95% of quantum mechanics with the harmonic oscillator and the coupled two-level system. So basically, the basic principles here, if you couple two systems, you usually, take two systems that are, if they are separated, they have, changing energy levels, and with some parameter Q, and there's some point where they are degenerate. If I now couple these two systems together, I get a different Hamiltonian, which I have to diagonalize, and you get this beautiful, as you have seen many times, the anti-crossing, which is connected to the coupling of the two systems. And this coupling of the two systems would then allow me, for instance, to automatically transfer from one system to the other by changing this parameter Q, and in the form of a lambda Zener transition. So this is basically direct coupling, and you find this is something which in a very more narrow way you call hybridization of two systems by making systems when you couple them, having this level repulsion and having lifting of the degeneracy. Same thing is you have two single wells, you put it together, and a double well, you get a double well coupling. Yeah. Now to implement something like that, I need a relatively strong coupling, because I need, in fact, this calculation is very simple, and it's without any decay of these states, and assume that these states are stable states, and then you have to get some kind of a rate how fast you can couple the systems over, which is given by this level spacing. Yeah, and so basically you have to be able to do everything faster, or you have to do everything. You have to make this pretty large so you can do a fast transfer of information. There are two ways to do that. One which is making your single qubit you want to transfer interact many times with your system, which is cavity QED, or take your system, the qubit, and let them interact simultaneously with many of these atoms. And I will come back to that later. First of all, this seems to be a much easier and cleaner way to do. There's a single atom sitting here, for example, and a photon coming in, and you couple it, and if you have strong enough coupling, which means that the coupling is stronger than the decay rate of the atom and the decay rate of the cavity, then you can transfer information into the atom. And that's usually characterized by something like the cooperativity, which is in fact good for cavity QED experiments. I think for looking at hybrid systems, cooperativity is not a good parameter, because you will see if gamma or kappa, if one of those twos is very, for instance, if this gamma is basically zero, like for an electron spin state in a solid, which has an extremely long lifetime. You know, electron spins in nitrogen vacancies have hours lifetime if they are cold. Yeah? Then it would be trivial to get a very large cooperativity, even though with a very weak coupling. And so you cannot really transfer systems in a good way. So in that sense, why I think it's much, there is no, as I tell you, I will tell you that there's no general way of how do I characterize a hybrid system when it's good and when it's not. So for each system you have to look at different things. Maybe we can come up with a cool way of doing that. That would be very interesting. So I have so you want to have the coupling strength to be much larger than kappa or gamma. And the other thing is that, which in at first looks like completely crazy, because you prepare a system like this one in a superposition of everything in state 1. And then you send a photon in there, and the optical density is very high. This photon will have a 100% probability of being absorbed. And this photon, when it gets absorbed, it can either, this is the second one is also long-lived state. You get a superposition between state 1 and 3, but you can do it, then it goes down, and then there has a superposition between 1 and 2. And when the photon gets absorbed, you get a photon of a different frequency out, the Stokes photon. And you would think first, this is the crazy state, because this superposition is a state like you have state 1, plus this massive superposition, which is something like 10 to the 10 particles here, where one of them is excited, yeah, with phase factors in front of it. And we'd assume that this state is really, horrible. You don't want to work with it. But it turns out that if you keep them in a clever way, the coherence properties of such a collective state is as good as the coherence property of a single state. And you can see that in such a way that, for instance, if I lose one of these atoms here, then my probability is basically, 100% that I lose one of the atoms which stays in state 1, and not the one out of the 10 to the 10, which is in state 2. So loss is not really, killing my superposition here compared to the others. But I will go back to that. So here you have to have very, very dense optical samples, and here you have to have very high optical finesse to get a very strong cavity. Now let's look at that. The first thing, if you take a quantum interface between, say, a single photon and an atom, you work in we come to a regime of cavity QED. You have this evolution is given by the James Cummings model, and which tells you, a photon coming in and exciting the system, or the system coming down and emitting a photon. And you achieve strong coupling, as I said before. And if you take an atom-light coupling, you see that this coupling is nothing else like the electric dipole moment times the vacuum field in here. And the dipole matrix element you can calculate in the atoms, and the vacuum field you can calculate in the vacuum field. What's interesting to see in there is that the vacuum field is given by a square root of you have one of the volume with omega and one of the volume. So if you want to make a large vacuum field, you have to make a very, very, very small volume of the cavity. So the coupling strength only depends on the volume and does not depend on the finesse of the cavity, so to speak. Yeah. Whereas the kappa then depends on the finesse of the cavity. So the thing is that to get very strong coupling, you have to get a very high finesse to get a small coupler, get a very small mode volume to get a large G, and you get a large mu, which would be either, Serge used the Rydberg atom here. Yeah? And large, small mode volume, which was a few lambda cubed, and a very high finesse kappa to do this very beautiful experiment of coupling photons to atoms. So for that, but if you want to do that with optical photons, for example, you just have to go into microcavities. You have very small cavities, like you have a fiber Pirot cavity, can have volumes that are few cubic. This typically is that what's the number, how big is the volume compared to the wavelengths cubed. And so we have about 5 here. You have these whispering gathering modes, can be also very small. Photonic crystals can be extremely small. These cavities, macroscopic cavities are a little bit larger, but in very, very high Qs. So this is a technological challenge, and you can make them right here. So I think one thing is here, okay, I can take these systems and couple them with optical cavities. You have photons coupled there, you can put atoms there, you could put spins there, they have optical transitions. But, these things are difficult to couple with optical cavities, but they couple very nicely to something, it's called a transmission line cavity, or a microwave, a circuit cavity. And this is something that came out, I think, out of radio astronomy, because these cavities were used as photon detectors. And let's assume you have a transmission line. That's basically a wire for a microwave. And you have a ground plate, and you have your wire, and this is a 50 ohm wire, and if you make 2 gaps in there, these gaps are like tunnel junctions, and these tunnel junctions allow you to make depending on how big this capacity is here, you get a transmission probability of the microwave photon going in here, so you can build up a cavity in there. Now, if you do that out of superconductors and aluminum or niobium or things like that, you get resonators that have a finesse which is 10 to the 6, or I think now people can go up to 10 to the 7 in a circuit. Yeah? This gives you a very high finesse, but the other advantage is the following, is that the electromagnetic field is confined to a one-dimensional geometry, which is typically one wavelength, or it could be half a wavelength long. Yeah? So it's typically a wavelength long, but this is, for microwaves, this is centimeters. But the transverse dimension is given by this gap, and that can be a few microns. So you get an extremely small mode volume, something like 10 to the minus 6 lambda cubed. And so even for a low frequency photon, like a 10 gigahertz microwave photon, you get large fields. You get fields in the range of millivolts of volts, electric fields of volts per meter for a single microwave photon, or 100 microgauss for a single microwave photon. So take a Cooper pair box that would be coupled with 100 megahertz or Rydberg atoms with 100 kilohertz, and even an electron speed would couple with about 100 hertz or something like that. You can be more, more fancy and build, circuit, a resonator circuit, which has this being the inductor and this being the capacitor, and then you can get the electric field more to be connected here, and the magnetic field more to be connected here. So you can improve these numbers of the fields by something like an order of magnitude. And you can use like loop resonators or things like that to improve these things a little bit. But I mean, this is something like how you get so you can get these resonators. So here you have then a second way of a microwave cavity, which would then couples very strongly to these systems and also to mechanical systems. And let's put the mechanical systems in there. So, and then, but also could couple to atoms or to spins. And now the question is that, can one use that also to couple to photons? And so, then there's the third transducer, which we can put in there, which is a mechanical system. And mechanical systems, you can bend one of those resonators by putting light on there, and by charges, you can put some magnetic particle on there by magnet, by gravity, by some inertial forces. You can also you can bend these things, and you can read this out by optics, or you can read it out electronically. So these mechanical systems, if you keep them quantum mechanically are perfect transducers for like electric fields, magnetic field charges, and things, or sensors, into an optical detection and readout. So you can think of, say, that you couple, say, magnetic spins to the displacement of a mechanical resonator, and this displacement of mechanical resonator is read out by light or read out by electric. And you can take a magnetic spin and couple them directly to light and couple them directly by this mechanical system. And I think chemists will talk a lot about various types of systems using nanomechanics. So as a third way, I think, of this bus, you have nanomechanics. And you can view that as some kind of a phonon. Yeah? You have the phonon inside the ion trap, which mediates interactions between distant ions. And here you have the phonon inside a nanomechanical system, which could mediate interactions across the type of systems. Now, these are the basic interactions. And now the question that we have to ask is that what happens if I have, if these interactions are still very, very weak? And there I stole a few things from Klaus Möller. Basically, what you can do is you can do something that you couple not to one system, but you couple to many. Let's assume, as I showed before, for the entangling part, you can take, let's put many atoms, and everything sits in the lower state, in state 0. And then if I couple them, then I can couple to each, and and if these atoms are independent, it's not important, they are independent. Now I couple to each of those independently. So in each of those, so if I do make the coupling, then I get, the coupling produces me a superposition state between state 1 and 1 over square root of n, some kind of phase factors in front, and it's the first atom is in the state 2, the second or the third, and this is a huge assemble, and this happens, in each of them can couple. So this happens 1 over square root of, so the system, if I take this system and couple it to that, it's a superposition 1 over square root of n times that. Now I can look at it, how strong can I do this coupling? So basically means I get my excitations being completely dispersed among 10 to the 8 or something, or 10 to the 10 subsystems. So Klaus always calls it the superspin. Yeah. Then I have my spin. Now see how strong is this interaction. We take now this interaction in there. I see that coupling to the superspin is enhanced by square root of n. Because each of those couplings here is, you have n of those couplings, so the total coupling is enhanced by square root of n. So the square root of n enhancement of the coupling strength, if I couple to n systems. So if I take, say, if I couple an electron spin to a superconductor, an electron spin to a superconductor has only a magnetic coupling strength of, say, 10 Hertz. But I have 10 to the 12 electrons. I get a collective coupling to that collective states, which is 10 megahertz. Yeah? So in principle, I can use that to enhance my coupling. Now, the Hamiltonian should be invariant on the permutation among the particles, and I mean, this type of Hamiltonian is the basis of many beautiful things like slow and stopped light, quantum storage and teleportation with ensembles, quantum speed squeezing, quantum repeaters, and precision probing and magnetometry. And so you can also say that one of those large superposition, one of those ensembles is like being a superatom, which is a much, much larger structure. Now, what are the key questions if I use something like that as a qubit? Yeah? So I could say this is my state 0, this is my state 1, and this is my superqubit, and I basically get this superposition state. Yeah? One question is that, how do I restrict this coupling to only, that I have only one excitation? Because in principle, if I just take an electromagnetic field and shine it in there, I will get coupling to many of those, and I would not create a single excitation in the system, I would create a coherent superposition of many excitations. That you can do, say, if you have this and you couple that to a superconducting qubit, you can do that because the superconducting qubit gives you only a single excitation. So the quantumness comes in because I have only a single excitation. And I don't make it classical. If I take a laser beam, I'll make a classical excitation and send a single photon in there and make only one excitation. Or I can post-select on only a single excitation. Now, what about inhomogeneities? Of course, if this system is inhomogeneous, then each of those systems will have a different evolution. Then each of those phase factors in front here will have a different time evolution. And then this superposition completely is destroyed. So you have a dephasing of the system, but we know as long as these different systems are completely independent and they don't interact with each other, we know how we do that from NMR. We can make a Hahn echo, or make a Ramsey sequence, and we can regain this type of information at a specific time. We can get back all our coherence. So inhomogeneity alone is not the really bad thing. Yeah? But then that inhomogeneity can also help us to encode more than a single qubit. Because if I apply now an inhomogeneity in the system to make a gradient along the system, then I make a very deliberate inhomogeneity in the system. Then this gradient will apply. If you write one qubit in there, it will dephase very, very specifically. If I turn the gradient back, it will rephase and will come out. Now if I change it, if I write one system in there with one gradient, and then write the next qubit in there with a different gradient, I can use such an ensemble. Then it's not a waste of using 10 to the 10 atoms for storing one qubit. So in 10 to the 10 atoms, I can store maybe many, many different qubits. I can make a multi-mode. I can use this many, many different times. The beautiful example of that is the storage of holograms in crystals. You know that there's this thing when you take a crystal, and there's beautiful experiments that are done where you can store a whole movie into a single crystal by storing it in different angles of a hologram. Yeah? And the same thing you have it here. You can take these methods that are used for this optical storage and for holography and things like that, to use into that, to put them into this type of systems. If there are no interactions between the systems. If there are interactions between the different systems, then everything becomes extremely complicated. So, and then the other question is, can we distinguish a collective excitation from the random excitation? And I think that's a really amazing thing, which surprised me in the beginning, and surprised, if you think about it hard, then of course it's not so surprising anymore, because you write an excitation in there usually with some very specific phase factors here. Any random thermal excitation, if there are many other atoms that are thermal excitation, will have a completely random phase factor. Now, if I need a Hahn echo to get a very specifically stored system out again, you will see that all the other random phases of the other system, of the other atoms where your information is not stored in, don't really matter, because they don't contribute to the readout. So basically what you have, with a quantum needle in a hot haystack, you have some kind of system which is completely messy. So you have 10 to the 10, you have 10 to the 10 atoms, or 10 to the 10 atoms, and you write a single, and if you optically pump them, if you extremely good optically pump them, you may get an efficiency of 10 to the 6. You still have 10 to the 4 wrong spins in there. But you write one single spins that are in there.
But the random spins will add noise.
They will add noise, yes. So that's another thing. They will add noise, will add fidelity, right, and something like that. But in principle, it's not for our first proof of principle experiments and things like that. That's not it.
I have a question about that actually. So one nuance would be that you want to distinguish between repetitive readout or ensemble readout and single shot readout. So does that still work in single shot readout?
You have to read each qubit in the writing. You can read out single shot. Yeah. I mean,
as long as you recover it back into a qubit. So
yes,
you can't read out the ensemble single shot. because all the other randomly
No, you have to, you read out, you transform it back.
Execute
Yes.
it, and then you can read it.
Right, that's very good. You have to be able to transfer it back.
Yeah.
Because a single one you will not find.
Yeah,
Yes.
exactly.
Yes.
Okay.
Yes. Thank you. Yeah. Right. Yeah, but I will talk about that in this round memory. Then of course you can combine both of those, which is you put many of these atoms in a cavity, and then you get you can get a very strong coupling and get ultra strong coupling, and you can even get systems where the coupling is stronger than the frequency, and so you can realize thinking models, and there's beautiful physics to be done, but I don't want to get phase transitions and everything in there. But if your coupling strength becomes too strong, but if you take weak coupling in a cavity, you can use the cavity to enhance it. So you combine all of these type of systems. So if you put all of that together, and this is now one of those figures, and which we got invited to write the perspective article for the proceedings in the National Academy of Sciences, and this is what we put on there. So you have you can think of all different types of systems, and you have couplings that are very strong, like between the superconductor and the microwave resonator. There are couplings that are ensemble couplings which are strong between spin ensembles and the resonator. There are couplings which are you can put together with where you have a laser that helps you coupling them together. Nanomechanical resonators. Nanomechanical resonators can couple to optical. There are many different types of resonators. You can couple phonons to optics and things like this. You can use Rydberg atoms where you couple systems. You can get them everything. I think to get them to propagating photons, you're going to have to go to either an atomic ensemble or go to a resonator. But if you want a very long storage, you want to end up here. So it's going to be a long way of going to various types of things to go through there. And I hope we didn't, we hope we put in most of the couplings that are there and most of the things. So you see that there are many different pathways, but it's not a trivial way of picking your correct systems. And I think we will hear a lot about, some of those type of couplings, and some of them might not. Very few are most of them, as they are done, as I showed here, are already explored experimentally, but not on the level that it can be technology with it, but just to show that these couplings exist and things like that.
So you said it's a paper in PNAS?
No, it's under. Yeah, we have to send it back.
Okay,
it's not yet. It's not yet.
Okay.
But we should. We have to send this with the it's a perspective article. It's not really many formulas, but it's just a.
No, but I want to steal this figure.
You can have it. In fact, I got it last night from Peter Rahman. So we sat together to finish it on what to do, and he did it during the time I was on the flight. So you guys are the first ones to see it anyway. Yeah. I haven't bought the Adobe Illustrator file if you want. So yeah. So let me go now quick over some of the examples of these type of systems, and then you can go another 10 minutes or something.
Yeah.
So of course, as I said, if you want to couple spins to photons, use cavity QED or circuit QED. Use ensembles of spins and collective states. You can use electrical or magnetic interactions. You can use Rydberg states. Or also virtual transitions. And there's a whole bunch of literature out there. There's nanomechanics. There's many different things that you will hear, very, very special things. They are beautiful of optical microwave conversion. You can couple an NV system to a phonon, and I think you will see many of the things in nanomechanics is will be one of the key players, I think, in there, which is really nice. You can do now really quantum mechanics, and I think Markus Schmiedmayer will tell you a lot about it. So. And as you saw before, oftentimes it will be a multi-state process to transfer this information in there. Now let's look at some of the things where the whole systems, the whole idea started. Was always the question of how to couple a microwave photon to quantum memory. And so, so there are many different things. You have a microwave resonator, and which has a strong electric field on this side, it has a strong current or magnetic field in here, and so you can put phosphorus donors in silicon, which is electron spins. You can take NV centers in diamond, which you put there. You can take rare earth ions somewhere in there. You can put molecular magnets on there. You can put electron spins in there, and whatever you think that can couple, then you will get enhancement. Typically, you get a single electron spin. A Bohr magneton couples with, say, 10 to 100 hertz to this magnetic field, and a Debye couples with if you're very close, coupled with 100 kilohertz to that. And so you can make a collective coupling to get this square domain enhancement, and you can get from hertz to megahertz coupling strength. And because these resonators, they are single wavelength size resonators, so even with a Q of 10 to the 6, then the lifetime of the photon is only a few hundred microseconds. And there are lots and lots of different groups who proposed experiments and who did experiments, and I will show you some of them in my last lecture. But as a teaser, there's all these different sets of superconducting qubits. This is Yale, Delft guy, or this is Martinez. And you can either couple a superconducting qubit via the resonator to a system, or you can couple it directly to a mechanical resonator, or you can try to couple it directly to a spin ensemble through a quantum, to the optical, to the microwave resonator. But you can, so these are experiments, these are diamonds on this resonator, and you can see, you can write systems in there, and as you see, these experiments are basic, so you see that there is some kind of coherent coupling, but it's nothing like you would now use from ion traps, where you see hundreds of thousands of oscillations. But in principle, you can see that there's a coherent coupling. The other part, but we can also couple directly if we take a superconducting loop, which is like a flux qubit, and you put an NV cent on top, then you get a single coupling. Because this is an extremely small resonator, you get a single coupling of 8 kilohertz, and you can collective coupling of 70 megahertz, and you can see beautifully the coupling between that, and there's even a dark state in there, and so you can find all type of funny, nice physics to do that. Now, what are the challenges if you want to do that? The challenge is you want to bring systems together. Of course, there's very different time scales. Nuclear spins interact very weakly and have a very long coherence times. And you want to write a microwave photon in there. There's a very short coherence time with the microwave photon. There's very different time scales you have to bridge, because you want to get something that is very fast to something that is very slow and very stable. There's usually also very different energy scales you have to bridge. For example, if you want to convert an optical photon to a microwave photon, there are 6 orders of magnitude in energy scale to bridge. And so there's also questions of that. For example, it's very simple to couple and to measure an atom, to use an atom to measure a superconducting flux, because if I use an atom to measure my magnetic field, I have a sensitivity of 10 to the -5 flux quanta. Yeah? But it takes the atom to measure that by mechanically move, for example, into the system, or by using this by mechanically moving the system, into the system because of its very low energy. It takes a much longer than the lifetime of the qubit is. Yeah? Otherwise, I would have had a perfect field of any superconducting qubit by just measuring magnetic field using say a BC as a magnetic sensor. Yeah? But it just doesn't work because the time scale is not good. You have to look at large coupling for faster systems, weak coupling for longer coherence time. So this is, I think it's every time. The problem is that we tried very hard in this overview article to come out with an rule of the thumb, like you have, okay, this is what you have achieved then you can make a hybrid system, and we didn't find one. The only thing we can say is that the coupling strength has to be larger than in the case. Okay, this is trivial, yeah. This is trivial, but something like cooperativity or something, little thing we didn't find out, maybe we can discuss it here, or we find something. There's, which works for all, for the complete set of systems. I would have liked to show you, okay, guys, this is the thing. If you get to that part of the thing, this is how you can couple it together. The only thing I can tell you is that, try to get to the trivial one, which is the coupling is much stronger than the decay times, and try to get there. And I mean, there's many applications in it. Yeah. The questions that are, I think, that we raised to consider what is needed to make a quantum hybrid system useful. For the moment, it's beautiful physics, and I love it. It's really, really fun what you can do. But it's also a question. Sometimes you ask yourself, will it have it, will it be useful for something sometime? And so it would be great to find, to really pinpoint where it's completely useful. For example, I had a long discussion with Matthias Teuer before Christmas, and he basically said, the superconducting qubit guys, for the moment, they don't need a quantum memory. They think they can do everything with error correction. Yeah? So, but the question is that, when, if the overhead by putting the hybrid system makes the error correction much simpler, then it will be something. But there's no clear, I cannot put my finger there, whereas there are hand-waving arguments. What is good, but hand-waving arguments are good if you start up a field, but at the end, sometimes you need to have, after 5 or 10 years, you need to put your fingers down and say, okay, this is what it is. I think where hybrid systems will be really, really useful is in metrology.
Right.
Yeah? Metrology, I think there we see many of the things, especially if you can use nanomechanics as a sensor or as a transducer and things like that. I think there will be many problems. Yeah? That we have any time. And as that quantum information, there's this big question between quantum memory and error correction. And Rainer Blatt always says, I need the quantum memory. I want to, at the end of my career, I want to make an experiment where I can keep the qubit alive as long as I want. Yeah? And so that's, and I think, but it's fun experiments, it's fun systems, and it's, I think, so I want to stop to that.
Thank you very much.
Yeah.
So I think that we should take a little bit of time for questions, but again, as Hossein said, the lecturers, the professors will be here the whole time. But if you have any urgent question, a big advantage of asking questions now is that other people probably have the same question as
and
well.
Also the question is, if there are now some very specific questions that I can put them in my lecture too.
Right.
So that's also one of the things.
And you should
do that. I don't know if I can answer them. Most probably do not answer them, but they are hard.
You have a question.
Yeah, can you elaborate a little bit more about the future in quantum error correction versus memory as we're talking about? What does it take to understand which one is what we should be aiming for? Yes, I understand that right now there's only hand-wavy arguments, but why do we only have hand-wavy arguments?
Because a complete calculation of what you need to do error correction is extremely hard. And what people did up to now are calculations of error corrections on the quantum side. Nobody ever calculated how much of classical resources do you need to do that. People think that the fastest now existing supercomputers will not be fast enough to do the classical control of that system. Yeah? If you would ever have one. So, and then you have to connect them. So that's one of the problems. I think it's going to be an experimental issue, which an issue of architecture. I mean, there's not very much known about real complete architectures of quantum systems. We have simple systems 1 and 2 and 3, and which we put together. There's, I think, the only really architectures that are really thought of more are these measurement-based quantum computation schemes, which are then go to these systems which implement topological codes. So there you have some specific architectures, and these are the only ones where people did calculations. Yeah, and so building a system, I think this is another thing. Systems engineering, quantum systems engineering is completely and it's interesting. You know, we are happy if we can make 2, 3, 4, 5 systems and couple them together, but it's nothing like, you know, and for system engineering, to build a really large quantum device, you need a couple of thousands of them. And, you know, you never know what the interference is. And now you put these 5 in such a way that they don't interfere with each other, but you cannot do that if you have 100,000. So I think it's a complete open question. It's an interesting part. And for the hybrid systems for the quantum memory to be useful in that sense, if you have a very robust coupling that is easily technologically implemented to make a memory for a superconducting system or for an ion trap or something like that, would help a lot. Or for an ion trap, if you have a system that can connect many of them together, yeah, or for a superconducting system where you can write a quantum information on the qubit into a memory and it stays there for 20 minutes and you then have to look at it. That will reduce the overhead a lot. But that's a system of real system design issue. Yeah? And I'm not an expert of that. So but this is what my friends tell me. And they say that basically people don't know.
Yeah.
So I have a trivial question. In conclusion, you said that you think that hybrid quantum systems are best suited for quantum metrology. What is the main advantage of quantum metrology as compared to the other metrology that already exists?
Oh, in quantum metrology, you would have the advantage that you can gain sensitivity, but that's only, say, in a regular measurement sense. If you can get more sensitivity by using larger systems, or if you can gain sensitivity by using more photons by measuring a distance, then it's fine. But if you get, by using more photons, if you get too much back action, like in LIGO, a gravitational wave detector, then quantum metrology will help you.
That's the perfect place to go. I was just like, you're going to say LIGO, you're going to say LIGO, LIGO.
Yeah, yeah. Yeah, or for example, there's this question of if you want to measure very locally microwave field, yeah, and you can measure that with a probe, but then if you want to put more, say this is it's an atomic spin, but if you put too many atoms together, they start interacting, and then you start an interactive many-body system, and you start defacing it a mess. But if you can use quantum metrology by squeezing the spin state, you get with 100 atoms the same sensitivity we get with 10 to the 4, and we could reduce all the other effects. So there are very specific things I think where quantum metrology will help you a lot. And if you want to get things like clocks, very high precision measurements, I think there it will help you. Maybe extremely precise measurement of magnetic fields in sensors or
I have a question going back to this earlier one that I wanted to, about this quantum memory versus error correction. So then you touched on briefly the ideas that I think are just really only within the last couple of years becoming discussed more mainstream, which is this whole notion of topological architectures. Some of them have been suggested how to do it in superconducting circuits. I think originally it came out of the nu equals 5 halves thing.
Yeah.
Right? So I don't have a great, I sort of understand the frustration between the quantum memory and I think I have a good handle on that one. I think most people that are working in the field have that handle, but this topological thing to me is sort of orthogonal. I'm not really completely, if you would say a few words, I would appreciate it. If you have any insight.
I can only say what we thought about how we make an architecture with MEs to implement topological codes, and I can only tell you what the guys who did that I was interested in how to build one of those nodes, what they need to do physically. Is it possible for an energy center to be good enough to do that? And the other thing is that the architecture, I can show you afterwards or something. But you know, they basically talk, but they also tell me that it's not completely known, you know, how good you really have to get these things. And it doesn't sound too completely crazy, but it sounds, at least it doesn't sound too completely crazy for people who work, you know, computer science. It doesn't. For an instrumentalist, it sounds completely crazy. As I said, 10 to the 10 physical qubits is not something that I ever wanted to do. But this is the 10. But you know, your iPhone is 10 to the 10 transistors. So yes.
You have a question.
Yeah. I was interested in your transmission line, your microwave resonator, with the transmission line approach, and I was wondering how, because you can have a left-handed system and a right-handed system, you can have backward wave propagation through a transmission line, and I was wondering how that could affect the atoms if you changed from a left-handed or a right-handed system to a left-handed system.
You know, I didn't think about it. I mean, there are all these now beautiful experiments from I don't know, Rauschenbeutel and others, where they have these one-dimensional lines for photons as nanofibers. And there, because of the structure of the Maxwell equations, you get into real selectivity between left-handed and right-handed propagating systems. How much this would also have an effect on the microwaves, I've never thought about it. You probably will also have some kind of an effect. Would have. So the question that how things are written down there now is in a very simple way, as it was written before AMO in regular cavity QET, where people never thought about these things. Yeah. But now, you know, if you have a confined electromagnetic field, you have to think about the staticity issues and things like that. But I've never, you know, we can try to work it out, but I've never, I think nobody ever worked it out. It would be cool to see if you can implement that in that way. Or you probably can do that in some way, because depending on how you engineer your ground plate and things like that.
You have the whole afternoon.
I have to say
But you know what? I think we should take a 5-minute or 10-minute break, relax a bit, get outside, and start again in 10 minutes.